Hello. Am I audible?
Yes, yes, you're audible.
We'll start at 3:05. Let's see if more people will join this meeting or not.
Good afternoon, sir.
Good afternoon, Karthik. Okay, I think we can start. Okay, am I audible to everyone?
Yes, sir.
Okay, so this is the week 3. So uh, I think in the classes we have discussed the Drude model by now. This was the first model that came out to explain the properties of metals, specifically the electronic conductivity, the thermal conductivity. So these are the two main properties which were studied next by the Drude model. So we'll start discussing the questions one by one. So this is the first question. Drude model for electrical conductivity measurement in metals failed because the electron collisions were neglected, the electron ionic interactions were not considered. It is assumed that the charge species are moving only on the surface of the metal, or it is assumed the charge species are holes. What do you think is the answer for this question? You can either unmute yourself and tell the answer, or you can also write it up in the chat box.
Option B, sir.
Option B, you're saying. Anybody else? Okay, so
Also option A.
okay, somebody said option A.
Also.
Anybody else? Okay. Now, so okay, we'll discuss this in detail. So this electron collisions are neglected. This is an assumption called the independent electron assumption, and this the one in which the electron and ionic interactions were not considered is called the free electron assumption. Now coming to option number C, so you have to understand that in 1897, so J.J. Thomson discovered the electron. J.J. Thomson discovered electron, and just after 3 years, in 1900, Jude gave this theory of uh, gave his theory to explain the uh, thermal conductivity and the electronic properties of the in case of metals. So he gave this model for metals, and he applied the kinetic theory of gases. He applied the kinetic theory of gases to metals. So what he considered that a metal is basically a gas of electrons. So at that time, the concept of hole did not even exist. So the charged species that were considered are electrons. Electrons are the charged species. So option D is wrong. And when it comes to option C, since it's a gas of electrons, it was considered that in the entire solid, each atom can give out an electron. which was called the valence electrons, and these valence electrons were later called the conduction electrons. So what happens is that in the lattice there are like ions which are positively charged because they have given out electrons, and they are all throughout in the material in the form of a gas. So the charged pieces are not on the surface of the metal; it is the entire bulk. So even option C is wrong. So only the first two were the assumptions made by Drude. Now to understand which of these options is correct, because I see somebody has mentioned A as well as B, let us look into some of the results that Drude got when he took this assumption. So if you look at, I think it was discussed in the class, if you look at the expression for the electronic conductivity, which is given by sigma, electronic conductivity, it is given as density of free electrons, which is the free electrons per unit volume, into the square of electronic charge into a time factor, which is basically the relaxation time or this is also the mean time between collisions. So this is like let's say this electron is there. If it has to move in any direction, so let's say it moves in the direction, then it hits an iron hair, bumps into an iron hair, it bumps into an iron hair, if it moves, it bumps into an iron hair. So this mean time or this mean distance, the mean free path of collision is in a few atomic spacings, which is basically a few angstroms. Now, one thing also we have to take care. Okay, now this also I'll just add this one more term. Like this mass of electron that is considered. So when say that the collisions were neglected or is not considered, it's not like what is neglected is some form of an ionic, like let's say a Coulombic interaction sort of thing. So physical bumping onto them is allowed. So if you would have seen it, so there is some kind of an average term which is added as a damping factor. If you would have seen that the it's written like m into dv by dt. So there's a electric field that is applied, and along with that there is a damping term, which is proportional to velocity. So there's an average damping term that is considered. So when we say neglected, it's the Coulombic interactions that are neglected. They're allowed to physically bump onto each other, where the Newton's laws are valid. Okay, now if you put in the values, so the typical values of NF are 10 power 28 per meter cube. But the electronic charge is known 1.6 into 10 power minus 19 coulombs. Tau, which is the relaxation time, is 10 power minus 14 seconds. It's an approximate value. And the mass of electron is 9.1 into 10 power minus 31 kilograms. If you put all these values, you get a sigma of which is basically the electronic conductivity of 3 into 10 power 6 Siemens per meter square or per ohm per meter, which is close to real metals. So if you see here, I don't have the data here. So if you would have seen the data for the conductivity, you'll see that this value is very close to this value. Now the thing is, from where does the error come? Like, now which is the error, electron collisions or the electron ionic interactions?
Sir, it's 3 into 10 to the minus plus 6, no, sir?
Oh yes, sorry, it's plus 6. Sorry, it's plus 6. It's 10 power plus 6 Siemens per meter, right? You are correct. So this is all correct with the experimentally observed value. So where is the error? Now, if you look closely, so we have discussed that this is the mean path. But what was actually observed is that the mean free path, if let's say L mean, actually if you calculate with the help of this like L mean by the Drude theory, you get it as in 1 to let's say I think around 10 angstroms. Like it will be in this range only. So this theory, this assumption seems valid that an electron will bump to another nearby atoms. But for this, I have to also like understand where were the failures to comment on which of these theories is actually incorrect and needs to be made better. So, if you look at the failures, the first failure is that the actual mean free path, the mean actual, is much larger than the Drude mean distance, and in fact, it could have actually gone to some centimeters of distance at a time. So if let's say an atom can travel, an electron can travel a centimeter of a distance, then this bumping of electron onto the ions, following the Newton's laws, is seems to fail. So electrons are not simply bumping onto the ions. The interactions are much more nuanced, and which has to be studied in detail. So here we see that the electron to ion interaction it has to be studied in detail. We cannot consider a average term and add it as a damping factor to our equation to find out the conductivity. Now, the second thing, so if you look at this equation where we wrote this, okay, I'll write it again. Sigma is equal to nf e square tau by m. nf nf e square tau by m, where nf is the electrons per unit volume, tau is the relaxation time, E is the electronic charge, and m is the mass of electron, each electron. Now here, for a particular metal, for a particular material or a metal, this E is fixed, this N is fixed, this M is fixed. So all of these are constants for a particular metal. So sigma should be proportional to tau. Now the way we define tau, see, is that if there are like, if there is a lattice of atoms, so this is the time that is required for electron, let's say, to move from here to here. This is the time, and or in a direction, here to here, or here to here, here to here. So there is no reason for this time to be dependent on temperature, because the distances between them is fixed. However, it was found that the sigma depends strongly on temperature. Just to see here, so these two are conductivity values at two different temperatures, and we see that as the temperature is decreased from the left to right, as the temperature is decreased, the conductivity shoots up. So there's a temperature factor here which cannot be explained by this simple collision of atoms theory. Moreover, we can go into further more details into it. The third thing, if you look at this same equation, so now for different materials at let's say the same temperature, the E will be fixed at same temperature, let's say. Then again the reaction time will be fixed. The mass of electron is again a constant. The electronic charge is a constant. So sigma should be proportional to NF. So as the density of electrons increases, the conductivity should also increase. However, here again we have a plot of electron density versus conductivity. We have the density here, which is NF, and this is the conductivity. We see that the data is all over the place. It is not actually linear. So this again cannot be explained. Like from where is this like this why is this linear behavior not followed up? Then comes then comes so now if you have let's say a lattice of atoms, let's say any FCC or simple cubic or any material in any crystal, it is seen that there is anisotropy in electronic conductivity. So depending on which direction you measure it or which surface you measure it, the electronic conductivity changes. And if metal is basically is a gas of electrons, and if only electrons are responsible for the conductivity, then why is the arrangement of ions making a difference? So the existence of ions, and to study that existence is also important. So the ions are important, which have not been studied in this model. And finally, in the case of alloys, if you look at alloys, something very interesting happens. So we have considered an alloy here. So if it's a copper and gold, like from 100% copper on the left to 100% gold on the right, we see that with an increasing amount of gold in the material, the conductivity initially increases, the resistivity increases. So it cannot be explained why it is increasing. And moreover, at in certain ordered components, there's a steep drop in the resistivity. It becomes highly conducting. So if the Duda model was correct, so at max, let's say if we had a resistive versus concentration plot, here we have 100% copper, and here we have sorry. So we have copper here and gold here. If copper resistivity was here and gold here, then with mixing we should have seen somewhat a linear profile, which we do not see. What we see is a highly like non-uniforms with steep decreases and sharp declines in resistivity. So this cannot be explained. So from all this, we see that if it was only a gas, then it shouldn't have mattered at all. But it is because of the presence of ions and then ionic arrangement. And this is where so even though we get the correct the results out of this electronic conductivity from the crude model, but this absence of the electron ionic interaction, because of which we see several inconsistencies with the actual data. So the correct answer is B. So I have spent some time in this question to make you understand that even though we have neglected this and we get the correct value of conductivity, some of the real life examples cannot be explained because we haven't studied the electron and ionic interaction. I hope you understood. Option B is the correct answer. Any questions on this, or we can go to the next question? Okay. So now we found out. So we found that it's around 3 into 10 power 6, right, for conductivity in the first example. So second one is an easy question. So it is exactly from the first question itself. Electrical conductivity calculated for a univalent metal system using the Drude model is of the order of 10 power 3, 10 power 6, 10 or 100. So we just calculated this. So we know that the answer is P, 10 power 6 Siemens per meter, or it is 10 power 6 per ohm per meter. So now we'll talk about heat flow also in the third question. So if we have two aluminum rods at room temperature, both of them are at the same temperature, and they're kept in contact with each other. So then the steady state heat flow from one rod to the other, which will occur by which mechanism? Any responses, any answers?
Steady state heat flow means we are not taking time into consideration.
Yes, you're right, but it's okay. Like, don't think too much about it. So, I mean, in which direction should the heat flow and by which mechanism? Let's not worry about the flow profile or anything at this point of time.
Okay.
So Tamagana said A. Okay, so if we haven't read properly, so both the aluminum rods are at the same temperature. They are kept at room temperature. So then the direction of heat flow. So okay, so we have this. Any answers? Okay, somebody said D. Yes, the answer is D. So Tamagana, I think okay. We'll discuss this here. So we have this Fourier's law of heat conduction, which says that okay, so this says that there is the heat flux is given by K minus K is equal to K dt by dx. So this is in one dimension, keeping it simpler for now. So the case thermal conductivity, dt by dx is the thermal gradient. So if both the aluminum rods are at the same temperature, then the dt is 0. At same temperature, dt is 0, and therefore dt by dx is 0, and therefore there will be no flux. So the answer is T. Now, if let's say we have this aluminum rod, and then we have this temperature of T1 here and temperature T2 here, and then if temperature T1 is greater than T2, and this is a solid block of aluminum, then what will be the mechanism of heat transfer?
No, conduction.
Yes, then it will be conduction. So the atoms will vibrate, and they will vibrate and give it energy to the nearby atom. Now let's assume now you have a pot of molten aluminum, and you are heating from this direction. So in this case, what is the mechanism of heat transfer?
That's convection.
Yes, in that case, it is predominantly convection. It is predominantly convection, because in this case, unlike in this where the atoms are tightly bound to each other, here they are loose. The aluminum atoms are loose, and then they can have a circulation and can transfer heat. At very high temperature, there will also be radiation, because each body radiates energy. That is why we have IR guns also to measure how much fever we have, because even we are releasing heat. So even radiation is taking place, but it's predominantly convection for molten metals, molten aluminum, and it is conduction when it's a solid block. So this is for solid, and this is for fluids. Now we have this. So now if you have an air conditioner in a room, then what is the process of cooling the room down? Is it conduction by blower, convection by blower, radiation by blower, conduction by vacuum? Blower is basically a fan. You can think it of as a fan. So, uh, how is the room cooled down when you have air conditioner in the room? Yes, it is convection by blower. I think so. It seems as like it is exactly same as boiling water or something. So this is same as boiling water, but in this case you're cooling it down instead of heating the air. So in this case, the cold air will come from the top to the bottom, and the warm air will rise up, and the warm air will go to the top and get cooled down. So that is how the room gets cooled with the help of a fan. So okay, so this is again. So if you're flying in an aircraft and at an altitude of 8,000 kilometers above sea level, so it faces more heat on one side of the aircraft. Like, does it face more heat on the one side of the aircraft because of the uniformly distributed solar energy? So again, if it is a metal, and if it is like if the solar energy is falling uniformly in all over the aircraft, then there is no reason for there to be a gradient in the heat, and so the answer is again false. Okay, so we had. I hope you understood this question, right? Hello.
Yes, sir.
Okay. I didn't spend much time because it's pretty much a straightforward question. Okay. So Fourier's law of heat conduction includes the negative sign in the formula, and why is that? Like because the heat flows from the cold to hot region, the heat flows from the hot to cold region. Gradient in heat is opposite to the direction of increasing temperature. Gradient in heat is the same as direction of increasing temperature. What is the answer for this question?
B and C.
Can you repeat?
Option B or option C, both are.
Option B, okay. Option B and option C. Okay, so we know that the option B is correct because we have already always seen it, that heat always moves from the hot to the cold region. So if we try to make a plot of, let's say, temperature and distance, if at a particular distance x1, distance x2, if the temperature here is like this at this point, and here it is higher temperature, and considering the like everywhere inside the material it's a linear increase in temperature, so we know that it's hot and it's cold. So this should be the direction of heat. Now if you take out the heat flux, J is equal to minus K dt by dx, you see that this dt by dx will give you a positive value, which means that the heat flows in this direction. But this negative sign corrects for that and changes this value to this opposite sign value to make both of this in the same direction, so that the direction of heat flow is correct. So that's why we have this negative sign to show that the direction of heat is from the hot to the cold region, and also the gradient of in heat is opposite to the direction of increasing temperature. Option C. All right, we'll move to the next question. So now we have studied the expression of electronic conductivity a while back. Now we'll discuss about thermal conductivity. So on which of these factors the thermal conductivity depends on? The mean square velocity of the electrons, the mean square velocity of the electrons and holes and ions, sorry, the electronic contribution to the heat capacity at constant pressure, electronic contribution to the heat capacity at constant volume. Somebody said A and D. So Tamagna said A and D.
A and C.
Okay, somebody said A
Sorry,
and C.
pressure, no? Sorry, sir, I'm not C. D itself.
Okay, A and D. So we saw that Fourier's law of okay, so somewhere up. So we had this Fourier's law of heat conduction, right? So we have this J is equal to minus K into dt by dx. And if you would have looked at the derivation of this thermal conductivity from the Drude's model, this K is given by 1 by 3 the mean square velocity of electrons. Then we have this again relaxation time which we had taken in electronic conductivity also. We have this specific at a constant volume. Because remember we are taking this electronic density per unit volume, or we have considered a particular volume to study the thermal conductivity, and so we don't consider the effect of pressure. We say that okay, this volume is constant, and in that constant volume what is happening. So it is a specified constant volume, and then we have dt by dx. So to go briefly into how these terms come, this 1 by 3 term comes because if taking heat flow in 3 dimensions, it's like x, y, and z. So it in an isotropic system, the amount of heat flow will be equal in all the directions in x, y, and z. But since we're taking only x direction, only one of them, so it will be 1/3 of the total heat that has gone in a particular direction. So we have 1 by 3 term here. This is the mean square velocity of electrons. This is the relaxation time. This is the specific heat. Constant volume. So from this expression we can see that isn't the Ruder's model, thermal conductivity depends on the viscous velocity of the electrons. So we have seen that we had considered the independent electron and the free electron assumptions. So the ions were not considered, and therefore this is this cannot be the answer because ions is not a part of the Ruder's model. And finally, we have considered the electronic contribution to the heat capacity at constant volume, which we write as Cv to the power with subscript superscript E. So the answer is A and D. Now to the 8th question. The Drude's model correctly predicts thermal conductivity of a metal since the contribution of lattice vibrations is important. Since errors in predicting mean time between collisions are cancelled by errors in predicting specific heat. Since errors in predicting mean square velocity are cancelled by errors in predicting specific heat. Since errors in predicting mean square velocity are cancelled by errors in predicting mean time between collisions. What do you think is the answer for this question? So, this like in collisions, specific heat. mean square velocity, specific heat, mean square velocity, mean time between collisions. So why is the two-day model able to correctly predict the thermal conductivity? We know that we have ignored the thermal vibrations because we are not considering any effect of ions, the free electron assumption, which is studied in the first question. So option A cannot be the answer. Which among the three is the answer? B, C, or D? Any answers, sir?
C.
Okay, somebody said C. Karthik, I think so.
Yes.
Mean square velocity and specific heat. Tamagna, Sakibur, which is Sabik, sorry. Okay. So from the Drude model, what was found out is that the specific heat at constant velocity, when we consider only the effect of electrons, was about the Drude model was about 100 times of the experimental, or let's say real values. Whereas the mean square velocity was about 1 by 100 times of the real value. Now, if you, let's say, take the example of a material, we'll see how with this with incorrect numbers, we reach the correct value of thermal conductivity. Now, let's say we take the example of silver. So I see that the molecular mass, the molar mass, is 108 grams per mole, and the density of this metal is around 10.5 grams per centimeter cube. Okay, so if we take the help of this too, so we can invert this number and multiply with this, and we'll get the how much moles of silver we have per cc. So 10.5 by 108 will be the moles per centimeter cube, and then we know that if we multiply this with the Avogadro number, then we'll get the number of atoms per centimeter cube, and from that we can get the number of atoms per meter cube. If we do that calculations, we will get how much we'll get. We'll get the electron number of electrons per unit volume as approximately 10 power 28, which we had seen earlier per meter cube. And we know that okay, and this is okay. This is the value of the electrons per unit volume. The specific heat that was found out by the Drude's theory was 3 by 2 into electrons density per unit volume into kb, which is around 12.5 joule per mole per Kelvin. Now, but if we try to find out the thermal conductivity, with this formula that we wrote earlier, 1 by 3 mean square velocities, then the relaxation time, the the specific heat at constant volume, we get it as around 12 10 power 2 joules per second per meter per Kelvin. Kelvin. Now see this. We have two values here. We have the CV, which is 12.5 for the CV, and thermal conductivity of 100. So if we compare the literature values, what the actual values, we see that the thermal conductivity. So we predicted this. We predicted it to be around 100, right? And if you compare with the values of different elements, we see that it is close to that 100 value. For lithium, we have 71. For sodium, we have 138. And for gold, we have 300. For silver, we have 400. So it is the same order. So the assumption somehow led to the correct values of the conductivity. Our K values are correct. But if you compare the values of specific heat of, let's say, of 12.5 by the calculations with the real values, we see that it is a millijoules per mole per Kelvin. So there is approximately 10 power 2 difference the values of the specific heat with the real values. So even though the velocities and the specific heat were the, the velocity and specific heat, the unit values were taken, somehow led to the correct values of the thermal conductivity. So the answer is C. So even though we made errors separating the mean velocity and specific heat, they cancelled each other because there is a multiplication here. They cancelled each other, and we got the correct results, correct value for our thermal conductivity. So now this question is again this is a follow up of the previous question. So thermal conductivity calculated using the Drude model is ordered 10 power 2 joules per second per meter per Kelvin or watt per meter per Kelvin. It is applicable for which kind of materials? Univalent metallic systems, polymer, copper, or glass? The previous question everybody understood, right? I hope there wasn't a...
Yes, sir.
Okay. What is the answer for this question? Karthik, Sabikur, Tamagna.
Should be A, sir.
Because somebody said A.
A and C, sir.
A and C. Okay, so the answer is correct. The answer is A and C. So if we compare with again the literature values, so it's 100 at joules per second or watt per meter per Kelvin, and we saw here that it's around the same values for all the elements. Even for copper, it's only defined by a factor of 3. So, but it's still in the same order. But if we compare other materials like polymers, glass, other non-metals, we see that these values are all over the place. They're nowhere close to being 100. They're not of the same order. They should be around 100 if the Drude model was applicable to them. And we see that it's for glass wool, the rock wool, for polymers, for non-metals. We are very far away from the Drude the Drude model's expected answers. So this is not applicable for non-metals. So the Dude model is applicable only for the univalent metallic systems and copper. It fits for the polymers and glass. Also, if you would have like observed, it's called the Dude theory for metals. For the metals, with the people were interested in knowing metals because they had this very unique properties of high conductivity, both thermal and electronic. They had a lustrous texture. That is why Dudes and other scientists wanted to know the physics of this metallic materials. This pseudo model is applicable only for metals. It is not applicable for polymers, glass, or ceramic or other kinds of substrates. We'll go to the next question.
Yes, sir.
Okay, so we discussed about electronic conductivity. We discussed about thermal conductivity. Now we'll talk about the Wiedemann-Franz law. So what is this Wiedemann-Franz law? It is the empirical relationship between thermal and electronic conductivity. It is the empirical relationship between the thermal conductivity and system temperature. It's said to be true for most metals. It is the ratio between electronic conductivities of two metals. Any answers? So, Wiedemann-Franz is an empirical law. What it means is that people performed experiments and then they compared, and then they came up with a model to explain this Wiedemann, this particular phenomenon. So it was given in 1853 by Wiedemann and Franz. So what they observed is that if you take the ratio of thermal conductivity to electronic conductivity, so it is equal to some constant of proportionality, let's say alpha, into temperature. So they saw that for metals, the ratio of thermal conductivity, the electronic conductivity, thermal conductivity by electronic conductivity is directly proportional to the temperature at which it is measured. And this value of alpha is more or less constant for all the metals. So we can compare the value of uh, k by sigma into t at different temperatures. And if you see here, this is the real data from a book called Ashcroft and Mermin. So if you look at here, this k by sigma t, this is what we have seen here, given by the Wiedemann-Franz law. It is more or less, see, it's more or less the same value for all materials, all metals. This is at 270, this is at 373. So this is an empirical law. So they saw that okay, it all fits. The proportion alpha is same for all metals at a particular temperature, and then they do this experiment at different temperatures, and they see that it varies linearly with temperature. So this is the Wiedemann-Franz law, and what they found out. So okay, so now we'll answer this question. So Wiedemann-Franz is the empirical law between thermal and electronic conductivity. Yes. So we relate this to uh, sorry. So we relate these to proper thermal electronic to come up with the which in the Wiedemann-Franz law. 1 minute. Huh. So we have related the thermal and electronic conductivity in the Wiedemann-Franz law. So it is said to be true for most metals. So we do not consider this. So it is not. It's not a relationship between thermal conductivity and system temperature. It's about thermal conductivity, electronic conductivity at specific temperatures. With temperature, it varies. And it is not the ratio between electronic conductivities of two metals. The answer is A and C. Now we come to the next question. So, with respect to thermal and electronic conductivity, which of the statements are true? Good electron conductors are also usually good thermal conductors. Some poor electronic conductors maybe also conduct heat well. Only metals can conduct heat, or only thermal insulators can conduct electricity. Any answers? So let us take the example of two different materials, diamond and silver. If you compare the values of their uh, thermal conductivity, okay, it's around 2000. Okay, the units are watt per meter per Kelvin. So this is around 2200 for diamond. It's around 425 for silver. So some poor electronic conductors, because we know the diamond is a insulator or a semiconductor with a very wide band gap. So it's a very poor electronic conductor, but it conducts heat very well. And also we also know from the Wiedemann-Franz law that K by sigma is a constant for metals. So for metals, good electronic conductors can also be good thermal conductors. Now, there's one thing to notice is that for the case of silver, so the heat is transferred with the help of free electrons only. Whereas for the case of diamond, the heat is transferred by okay, free electrons plus lattice vibrations. Ideally, because even the atoms will vibrate, the ions vibrate about their main positions. But in the case of diamonds, it's lattice vibrations only. So the heat transfer mechanism is different for these two kinds of uh, heat transfer mechanism is different for these two kinds of materials. So, so for let's say for thermal conductivity, we both free electrons and lattice vibrations are important, whereas for electronic conductivity, only the free electrons are important. So we see that the mechanism of thermal and electronic conductivity are different.
Sir, whatever the statement we are making is at room temperature.
No. It is applicable at all temperatures. But if let's say there is a change in phase of the material, then you know the mechanism might change.
Okay.
Okay, so I've sort of like combined these two questions together to say that the mechanisms for electronic conductivity may be different from the thermal conductivity.
Yes, sir.
You understood, right?
Yeah.
Okay, so I think it's almost 1 hour. Let's see how long this Google Meet can go on. I have two more easy questions. We can go through them. If it stops in between, then maybe we can discuss next time. So these are some very general questions. So in the Drude model, we have considered that the only interaction between electron and electron and ion is a sort of a bumping of them with each other. So what is the manner of interaction of the free electrons with ionic cores? So it's known that the charge species. So the interaction will be Coulombic in nature. So you will be seeing that in the upcoming chapters, as well as in the upcoming assignments, that we will be discussing about how these electrons uh, are located in the energy level with respect to the reciprocal space. You'll be learning about all these terms in the upcoming lectures. So the interaction between electron and ion is strictly Coulombic in nature. And finally, uh, in all of this, we have considered the kinetic theory of gases. So we know there are different kinds of statistics: the Maxwell-Boltzmann statistics, the Fermi-Dirac statistics, and the Bose-Einstein statistics. Which of the statistics do we use to study this the thermal conductivity, electronic conductivity in the case of metals in the Drude model? Any answers? Any guesses? I know you haven't studied this yet. This will be discussed in the upcoming lectures.
Fermi-Dirac.
No, so that is what. So till now we have considered only the Maxwell-Boltzmann statistics.
Yes.
So, but we know that yes, Tamagana is right. It's a Maxwell-Boltzmann statistics. But actually, these electrons, uh, we have something called the Fermi-Dirac statistics, and when we include that, we see that our results are much more this model gives us results that are much more coherent with the actual real life observations. And so electrons follow this Fermi-Dirac statistics and not the Maxwell-Boltzmann statistics. So the kinetic theory of gases is not a correct assumption for modeling metals. So this is in the upcoming classes. Okay, so the Bose-Einstein statistics or the bosons. So the electrons are fermions, whereas bosons are a different class of materials. For example, this phonons and photons, they are bosons. They have they have a different spin quantum number. So you'll be studying about all these things in the next classes. I just thought, okay, I will just introduce it to you that there are different statistics, and the statistics that we're following currently, the Drude theory, is not applicable for the Fermi-Dirac. For the in the real life uh, electrons system in a metal. So I think it's past 1 hour. This Google Meet may stop anytime. I hope you all learnt something in this class.
Yes, sir.
Okay, so we'll discuss more about the statistics in the next class. We'll discuss about the Maxwell-Boltzmann, Fermi-Dirac, and the Bose-Einstein hopefully in the next class. So this is all for today. I'll be sharing this video on YouTube, and this file will be available online. Okay, thank you everyone. Thank you for your time. You can leave. We'll meet again next week.
Thank you, sir.
Okay. Thank you. Thank you, Karthik. Thank you, Tamagna. Thank you, Sabikur.